Okay, the recording has started now. I'm gonna go ahead and share my screen. Please let me know if you guys can see that. You see me marking up the screen too? Okay, awesome. All right, so yeah, like I said, these are the slides that I made for the chapter 5 like content stuff, all about free energy. Just kind of a general like checklist, I guess, to see what's going to be covered for these slides is just all the different types of free energy and how they can relate to equilibrium. And so I think the first step is to obviously define what free energy is. And so this is where I kind of go into the more like background stuff and the theoretical aspect of like what's going on here. So this is something that they don't quite, I guess, go into depth about in the lectures. But I think it's important just to kind of understand not every single piece is like absolutely essential. So if you get like super confused, like what's going on, don't worry. Like it's supernatural that you could supernatural. It's very natural to be confused about like this theoretical stuff because it hasn't been covered really in lecture and might be a little new. But the idea is that I think it's very important to just kind of understand at least some of it so you can understand kind of what's going on. Because if you understand the purpose of these equations, where they're coming from, how we're deriving them, I think that helps like solidify the concepts a little bit better. But just to preface this like set of slides, you don't need to understand every single like background piece of information to like do well with this topic. It's a very math, heavy kind of topic. So if you just know the definitions of each of the different types of free energies, the equations that pertain to them, and the conditions that you can use them in, if you just know how to manipulate the variables, what the variables mean, when to use each type of free energy, and when to use each type of equation, you're probably going to be solid. This isn't a topic that you have to like. I mean, there might be aspects that you do have to explain, and there are aspects that you do have to understand. But like, I will probably try and point out like, like I'll say like, hey, this section isn't like super important. Like if you don't understand it, like it's okay. But yeah, without further ado, I can go ahead and get started here defining free energy. So when defining free energy, we have to consider what the main question we're asking about in thermodynamics in general. So this kind of goes back to the first couple of weeks where we're trying to figure out essentially how a system evolves, right, over time. So if you have two parts of a system that aren't in thermodynamic equilibrium, the question is what will tend to happen to that system, right? So if you have those two systems, remember in earlier chapters, earlier units, where we're talking about like, okay, if you have a hot object and a cold object, right, the hot object will transfer heat, the energy will go from hot to cold, basically, right? So these are some of the answers, right, to that question of what will tend to happen. So mentioning that hotter object, colder object system, right? Well, if one part of a system is hotter than another, right, the system will spontaneously even out the temperature by flowing energy from the hot object to the cold object, right? And then with any of these systems, right, if you have one object hotter than the other and they come into thermal contact with each other, they will transfer energy, right, in that specific direction from hot to cold, right, in one direction until the rate of the reverse reaction is equal to the rate of the forward reaction, right? And so what that means, right, when you have the rate of the forward reaction is equal to the rate of the reverse, that means equilibrium is achieved at that point, right? So systems tend to evolve in ways that will achieve equilibrium, to achieve a steady, stable state where the rate of the forward reaction is equal to the rate of the reverse reaction, right? And where you have everything in thermal equilibrium, temperatures are equal between two systems if they had differences in temperature, stuff like that, right? Now, another question is, well, how does entropy come into play with the second law of thermodynamics, right? This is kind of review, and it's necessary review to kind of figure out what's going on here with the rest of the chapter, right? So entropy, we said, I don't know if it was last week or the week before, I can't remember, but that it's proportional to the natural log of the number of microstates, right? And the number of microstates for a specific macrostate, right, is the multiplicity, right? So this was the equation that we were going over last couple of weeks here, which is entropy, S, is equal to Boltzmann's constant, KB, times the natural log of your multiplicity, right? And we were talking about volumetric entropy volumetric multiplicities, energetic entropy, energetic multiplicities, right? So in general, though, that whatever type of entropy you're talking about, it's proportional to the natural log of the number of microstates, right? So a system not in thermal equilibrium, right, will transform to increase entropy, right? So kind of talked about this with the week 4 review that I went over, and you can check that on YouTube to kind of get an overview of what was going on for that. But essentially, remember we had the old definition of what entropy was. We said it was kind of like a measurement of disorder, right? And that the entropy of the universe is proceeding towards more disorder, essentially, right? That's an older definition. We can kind of combine it with a newer definition, and the newer definition is basically saying, like, okay, a system, well, even if it's not a system, if we're just talking about the universe will tend to move towards, right, achieving more microstates, achieving more positions, achieving more ways that energy can be distributed, right? By positions, I mean like positions, for example, like in a container, right? If you have a certain volume of a container, then the system that you were looking at, right, will tend to evolve, right, in a way where the molecules or the particles will be able to take up more positions, more locations inside, right, the container. So if, for example, we have, without looking at a container necessarily, but we look at like the water particles in an ice cube, right? Well, they're kind of, let's say, quote unquote, they're kind of like in a container. And so they're kind of tightly packed. They don't have much option to move. It's all very kind of localized positions, and they don't have very much range of motion, right? Now, spontaneously, that ice cube will melt, right? It'll try to evolve towards a more, I guess, what was I going to say? A higher entropic state, right? So it's going to move towards a state that gives it a higher entropy, right? Gives it more microstates, more ability to move, more ways to distribute and store energy, right? And we can think about that as disorder, quote unquote, or as chaos, right? Where if those water particles were packed super tightly in an ice cube, now when they melt and they achieve that liquid state, they can move around a lot more. They're more fluid, right? Because they're in a liquid, so everything's a little bit more spaced out, not as tightly packed. And then at the same time, right, they can distribute their energy in more ways, right? Because they can move a lot more than they could in the solid, essentially, right? So the idea is that for systems and for the universe as well, we're trying to achieve an increase in entropy, right? The systems and the universe will try to achieve a state of higher entropy, and that's what's going to happen, right? So, and if we connect that idea where entropy is proportional to the natural log of the number of microstates, right? Well, if entropy is related to microstates, then a higher entropy means that you have more microstates, right? So we're trying to achieve those greater number of positions, more ways that we can arrange those water particles, right? More ways we can store the energy of the water particles, for example, right, in that system. So the idea is that the macrostate with the highest entropy will be more likely to evolve than a lower entropy macrostate, right? So remember, macrostate is a big overarching event that has specific microstates corresponding to it, right? So the highest entropy will be more likely to evolve than a lower entropy, right? Because a higher entropy will have a higher multiplicity, right? And remember, the probability of a macrostate, probability of macro, is equal to the number of microstates that you have, or the multiplicity in this case, divided by the total number of microstates, right? Like the total number of outcomes, essentially. So if you have a greater entropy, remember we said entropy is related to the multiplicity or the number of microstates. Well, larger entropy means a larger microstate or a larger number of microstates. So that gives you a larger numerator here. That larger numerator will mean that you have a greater probability of your macrostate, right? So greater entropy, greater S, means greater multiplicity or number of microstates, therefore greater macrostate probability, right? So the macrostate with the highest entropy has the greatest multiplicity, the greatest number of microstates, right? And therefore greatest probability of that macrostate, and then that will be more likely to evolve to that higher entropy than a lower entropy. Does that make sense so far? Any questions? All good? Everyone else good too? Just want to make sure before I move on. You guys all have access to these slides, right? I make sure to upload them to the Google Drive. So if you want to like use them, download them, take notes and stuff, feel free to do so while we're doing it. Okay, I see another thumbs up. I'll take that as a yes, so I can go ahead and move on. But now in the readings, right, they bring up this concept of useful versus non-useful energy. So what is this idea of useful energy, right? So when you have a system that's in thermal equilibrium, right, when a system is in fully thermal equilibrium, right, we said that if you had a system with two parts, right, or even two systems that weren't in thermal equilibrium, were not in thermal equilibrium, then energy would flow between them until they achieved that equilibrium, right? So if they have achieved that equilibrium, right, then energy no longer flows from molecule to molecule, right, or from one energy type to another, right? So there's no longer a flow of energy from molecule to molecule or from one type of energy to another type of energy. There's no transfer of energy anymore in that sense, right? And so when you're at thermal equilibrium, we can kind of say that, well, at that point, the energy is then quote unquote useless, right? Both of these systems, both parts of the systems, for example, are just kind of at this steady state. They have their own respective internal energies, but we really can't use that energy to do anything because they're all kind of steady and there's not any flow of energy, right? So we call that quote unquote useless energy, right? So now we want to look at energy in terms of whether work can be done, right, instead of total energy, right? So when we were talking about energy before, the most common type, I guess, well, not type, but I guess most common concept when we're talking about energy is internal energy, right? And remember that was related, that was the U, and that was 3/2 N kBT. That was the total internal energy that a specific like system had, right? So instead of looking at total energy that a system has, right, just the regular total energy that it has, based on like number of molecules, based on its temperature and all of that, we want to instead look at energy in terms of, well, what can that energy do for us, right? Can that energy be used to do any work? So we're looking at, instead of that useless energy, right, that can't do work for us, that can't do anything for us, we want to look at the quote unquote useful free energy, right? That's why they call it free energy. It's free to do work for us, right? So we're not going to focus too much more about internal energy at this point. We're going to look at things relating to free energy, the energy available that's free to do work, rather than just looking at the total energy, right? Well then, we were talking about entropy, we're talking about free energy, right? Well, how does entropy relate to this concept of useful energy, right? What does that useful energy mean again? We said that it's that useless type of energy, or my bad, useful energy is the opposite, my bad, sorry. So let's talk about how entropy relates to useful energy instead of that useless energy. So if a system is at equilibrium, right? If a system's at equilibrium, then entropy's at its maximum, right? Like we said, a system will try to evolve itself, reach a point where it has maximized its entropy, right? Whereas basically try to achieve as many microstates as possible, right? Achieve as many locations that the molecules can take up, ways that the energy can be distributed, right? So at equilibrium, entropy is at a maximum, and then, like we said, there's no free energy. The energy is useless at that point. Work can no longer be done at equilibrium. But if a system is not at equilibrium, right, and that doesn't mean that it's like less than the equilibrium state, for example, like if we were looking at reaction quotient expressions, right, versus like equilibrium expressions, remember those from chem, doesn't mean that it has a less or more. It just means that in general, like if you're just not at equilibrium in general, then your entropy is not yet at a maximum, right? Work can still be done at that point if you're not at equilibrium, because there is free energy. There is useful energy there to be used for work, right? So that free energy can be redistributed, work can be done to get that system to that equilibrium state, right? So as long as we're not in the equilibrium state, we have free energy to do work, and that work can be done to get us to that maximum state of entropy, to get us to that equilibrium state, which is what we want. And like we said, the universe tries to achieve this point, and that's why we say, like, the entropy of the universe is going to be increasing, right? Now, just to kind of recap right again, difference between useful and unuseful energy, right? So useful energy, that free energy that can be used, right, to do work, to convert, for example, chemical energy into internal energy of other molecules, right? And this kind of makes sense, right? Because we were saying that, well, after a certain point, that energy is useless, right? And so that useless kind of state of energy is just whatever internal energy that the systems have when they're at equilibrium, right? So if you have those two systems that are not in equilibrium, well, then you might convert like chemical energy between bonds and stuff like that, between the molecules, into internal energy, right? And that transfer can happen through work. Like I said, free energy is the energy available to do work to achieve that equilibrium state and that maximum state of entropy, right? That unuseful energy is that free energy that's transferred or lost. Usually we look at that unuseful energy as heat. But that doesn't mean, right, because I said unuseful energy is often free energy transferred or lost as heat. It's often lost as heat, right? But that doesn't mean that there can't be useful heat or that there can't be unuseful work, right? Because we said that free energy can do work for us, but there's also unuseful work. We said that free energy can be lost as heat, right? And that makes it useless or unuseful, right? Free energy. But we can also have useful heat instead. So we're going to see this here in a sec, and how that useful, unuseful work and heat will make up a change in internal energy and free energy. So now we beg the question, how can we relate useful and unuseful energy concepts, right, to the first law of thermodynamics, right? Because remember, we're talking about changes in internal energy, right? So we said that chemical energy can be converted into that internal energy. Well, we want to see what kind of free energy change we're talking about, right? And how that can cause a change in the internal energy. Relate all those two things together, and also relate it to the idea of useful and unuseful energy once again. So the first law tells us that your change in your internal energy, delta U, is equal to the work plus the heat, right? That work, like we said, can consist of useful and unuseful work, and the heat can consist of useful and unuseful heat, right? So the equation can actually be expanded a little bit, because what we have here for the first law in that first week or that second week of concepts was just this general equation like this, right? Technically, if we expand this out, that work can be useful work, like I said, or unuseful work, and useful heat or unuseful heat. And that makes up the change in internal energy, right? How can we define then a change in the free energy, right? Well, the change in the free energy can be defined as such. So if we subtract the unuseful work, right, that unuseful work, and the unuseful heat from the change in internal energy, right, then we can get change in free energy. What that means is if you take your internal energy change, subtract over the unuseful work and the unuseful heat, right? So if we just did minus and minus, right? So delta U minus W unuseful minus Q unuseful, right? That gives us our change in free energy right there. And what you notice too is that, well, if you subtract those two terms over, then you're also left with free energy that can be defined also as simply the sum of the useful work and the useful heat. It's the expendable, useful part of energy, right? So change in free energy can be defined two ways, right? Sum of the useful heat and the useful work, or the difference between the change in the internal energy and the unuseful work and the unuseful heat, right? This equation, this concept right here, right? This idea of useful, unuseful energy. It's nice to kind of understand. It's nice to know. I don't think it's a horribly like difficult concept to understand, but like you won't. I don't believe you would be expected to kind of like explain all these different concepts of useful versus unuseful energy, and then go into depth about like an equation like this. Like you don't have to like actually plug these values in or anything like that. That I highly doubt. It's just nice to understand where this idea of free energy is coming from, right? But yeah, that useful energy, that useful free energy can then be spread uniformly throughout the degrees of freedom of the environment, and that energy can't be recovered again once it's lost, right? So that covers defining what free energy is, right? That covers what free energy is. Now, there are different types of free energy, like I said. You might have already seen some of those on the written homework already, right? But once again, we kind of have to just take bit by bit, re-explain some things, recap, make sure that we're still kind of fully understanding everything as we go along. And so we kind of should remind ourselves, how does a thermodynamic system evolve based on the first and second law of thermodynamics, right? So if any work is done by the system, the system will tend to move toward lower energy, right? Just think about it. If you're doing work, if the system itself is doing work, right, the work done by the system, it's transferring energy from itself, basically, right? Because it's in and of itself, the system itself is doing work. So it's going to be transferring energy from itself to the environment, essentially, right? So the system itself will then tend to move toward lower energy, right? The first law of thermodynamics tells us that energy is conserved then, right? Remember the first law of thermodynamics, that energy cannot be created or destroyed, it can only be transferred, right? So if that energy is conserved, and if a system can do work and essentially transfer that energy in the form of work to the environment, well, then how does energy of the system technically decrease if energy is conserved, right? How do we maintain that idea of conservation of energy if it seemingly, if the system does work, then it transfers or loses that energy essentially, right, to the environment? Well, energy can still be considered conserved because that energy lost from work done by the system, that energy we can still account for it because it's simply just transferred to the surroundings, right? So if we were to analyze the surroundings, the environment, we can account for that energy that was quote unquote lost, right, from the work done by the system. So the first idea, right, about how a thermodynamic system will evolve is that a system will tend to move toward lower energy. That's the first idea. System always moves toward a state of lower energy, right? So think about like lower energy, right? If in just more general like terms outside of physics, like if you have lower energy, you won't be able to do anything really, right? You'll be at this relaxed kind of state, right? You won't be doing anything, right? You won't be doing homework. You won't be coming to this session. So, like, you're just kind of in this relaxed state of lower energy, right? So particles, the molecules, whatever, come to this more relaxed, stable state, right? That lower energy is kind of an indication of almost like stability, basically. So the second idea, then, is that we expect the system, in this we mentioned before, to move towards higher entropy, right? Now, the second law of thermodynamics tells us that the entropy of the universe is increasing, right? So, well, you might be thinking that, okay, we've seen some examples maybe from the homework, right? Or maybe you've seen some examples maybe in your Gen Chem class or something that entropy, delta S, has been observed to be negative, right? That would indicate a decrease in entropy, right? Well, you might be thinking, well, if there's a decrease in entropy in the system, then how is the entropy of the universe increasing, right? If the entropy of the universe is increasing and the universe is essentially made up of different systems, well, if systems are decreasing in entropy, then how does the entropy of the universe still continue to increase, right? Well, and the entropy of one individual system could decrease. Maybe multiple systems could decrease. But if we were to add up every single system on Earth, right, in the end, the overall universe entropy increases, right? So that's two really important ideas here about how a thermodynamic system evolves over time. The system will tend to achieve a lower energy state that's more stable, and the system will try to move towards a higher state of entropy to achieve more ways that it can distribute its energy, more positions that it can take up in a container, for example, right? That's the idea of like energetic entropy versus volumetric entropy right there, right? So we want to achieve more microstates, higher multiplicities, therefore higher probability macrostates with higher levels of entropy, right? So that brings us now to the different types of free energies, right? Enthalpy delta H, Helmholtz free energy delta F, and good old Gibbs free energy delta G, right? Now, each of these types of free energies, right, you might be thinking, well, why the hell do I have to account for 3 different types, right? Free energy is just free energy. We already defined that as being energy that's expendable to do work, right? It's that useful energy. Well, the idea is that you have different states, you have different scenarios where these energies could be applicable. And so we have these different types of free energies to be able to specifically and accurately define, right, the free energy depending on different states of your processes, right? So remember, we were talking about earlier in the semester about different processes like adiabatic expansions or isochoric cooling, right, or isobaric processes. Well, each of those different processes will hold specific variables constant, right? So isobaric processes will hold pressure constant, for example, right? Adiabatic processes will not allow heat to flow, for example. There'll be different scenarios, different situations to where these different types of free energies will be applicable. Each one will cover or be able to describe the free energy depending on the variables that are held constant or the variables that are changed, right? So first, let's start with enthalpy, right? What is enthalpy exactly? Well, it's one of the forms of free energy, and it's used, or we analyze it, when we have constant pressure and temperature, but a changing volume, right? So think about enthalpy as whenever you have a situation, a scenario, a process that has constant pressure, constant temperature, but a changing volume, right? Common example of when we use enthalpy or we analyze enthalpy is that if you're looking at a piston or a container with an adjustable lid, and I'll go into depth with that here in a second, right? That's the most common example that we use when thinking about enthalpy. Now, with regards to enthalpy as a free energy, right, a form of free energy, well, there's no transfer of unuseful heat here, right? Because whenever we're using or looking at enthalpy, we're looking at scenarios or situations in which we're actually controlling the heat, right? So usually in these types of examples, we'll have maybe like piston filled with water, right? Or maybe like a container with an adjustable lid that we're filling with water, and then we're actually boiling that water, right? So when we're boiling that water, we're actually being able to control the heat, right? That's the idea here. And so because we're controlling heat, there's no transfer of unuseful heat, right? And then in the case of enthalpy, only PV work, pressure volume work, right, is done. And this work, we note it as unuseful work as well, right? So for enthalpy, there's no unuseful heat, but the PV work, we define that as unuseful work, right? So remember, when we're looking at change in free energy, we define that as either the sum of the useful work and the useful heat, or we could also define it as the change in the internal energy minus the unuseful work minus the unuseful heat. Well, like we said, there is no unuseful heat because we're actively controlling the temperature or controlling the heat, right? And then only PV work is done. And so that's that unuseful type of work. Now, you don't have to quite understand the idea of unuseful work, unuseful heat for these different types of free energies. I'll go over them anyway, like in each one, explain as best as I can. But if you just understand this equation, what this means, right, you're solid. If you can understand the variables in the equation, if you can understand what they mean, how to manipulate them, how to move them around, you're good. This idea of unuseful versus useful energy for each of these types of free energies, it's nice to understand. I don't think it's a horrible concept, but I can understand where it kind of can be confusing. Honestly, it took me a while to fully understand it too. So if you just want to go ahead and look at these equation, figure out what it means, the terms in it and stuff, you're going to be solid. That's not going to be a huge issue anyway. Like I said, it's very mathematical based kind of, I guess, focus here with this topic. So it's mainly, do you really understand what these free energies are, roughly, what scenarios they're to be used in, what the variables are for the equations, stuff like that. How they're derived, I think personally it's nice to know to be able to solidify the concepts, but it's not absolutely necessary. Once again, just keep an eye out. They're, like you've seen already on the quizzes, they ask you to explain certain concepts, and they will ask you to explain certain concepts on the exam as well. So that's why I always feel that it's nice to understand where all this stuff is coming from, just in case you're faced with a question that asks you to describe this stuff. And so if you don't understand the background, you only know how to do the math, well, you might be screwed for that question. Now, granted, those types of questions might only be like one part of a question on an exam, or two parts, right? But, you know, if you're screwing up on the rest of the exam, it's not a good thing to like also screw up some easy points like that. Because if you know how to manipulate the equations, you're already like 80% of the way there. The other 20% is just really just trying to understand as best as you can where this stuff is derived and, you know, how to make sense of it. And so, like I said, I'll explain it. If you're not 100% getting it, that's totally fine. You can try and go back and watch the video again. Maybe if you just kind of slow it down on your own pace, that'll help. Or, like I said, you can try and ask me right now. If you guys have any questions, I'll try my best. But even like myself, like it's just sometimes it's kind of hard to explain where this stuff is coming from because I'm referencing the same information that you guys are. So I'm using the readings as well to derive my knowledge. And so I'm not perfect, but you know, I'll try my best. But like I said, if you know this equation, you know how to manipulate it, all that stuff, you should be solid. But yeah, so that change in free energy, right, that doesn't have a transfer of unuseful heat, but does have unuseful work in the form of PV work, pressure volume work, we define that as enthalpy. And enthalpy, once again, is when we have, it's a form of free energy that we look at, right, and we analyze when we have constant pressure and temperature, but a changing volume. Constant pressure and temperature, but a changing volume, right? And so you end up with delta H is equal to delta U plus P delta V. So this change in free energy, delta H, is equal to delta U minus that unuseful work, right? And the unuseful work is that P delta V. Now, if you remember, right, if you remember from an earlier chapter, that work, that PV work, was defined as W equals negative P delta V, right? So when we say delta U minus that unuseful work, we're saying delta U minus negative, delta U minus negative P delta V, right? And so that gives you that positive right there. That's why it's positive. Now, continuing on, what is enthalpy, right? That PV work is the energy that must be added to the boiling water, right, to change the volume of the container or piston. Because think about it, right? Like, for an example of the enthalpy, right, that piston, that adjustable lid, you could have that piston or container freely expand or contract, right? If you boil the water inside, like we're doing, right, where we're keeping this heat controlled, right, so we don't have any unuseful transfer of heat. If we boil the water, you're adding heat into the system to break bonds that convert the water from liquid to gas, right? Well, the idea is that the just adjustable piston, right, or the lid, will help maintain a constant pressure inside the container, which is that atmospheric pressure, 1 atmosphere, right? So having that lid there helps to kind of maintain a constant pressure equal to the atmospheric pressure. But the more you boil that water, right, the more particles that are converted to a gaseous state. Therefore, the vapor pressure inside the container here, right, will tend to increase. And so the pressure inside the container increases overall, right? Now, with the pressure increasing here on the inside and the lid trying to maintain that atmospheric pressure, well, like we said, because it's an adjustable lid or an adjustable piston, if the pressure inside the container happens to increase to a point where it's greater than the outside atmospheric pressure, so pressure inside greater than the pressure of the atmospheric or the outside, right? Well then, we see an increase in volume, right? Why do we see an increase in volume? Well, remember, pressure and volume are inversely related. So let's say that pressure on the inside became 2 atmospheres, right? Became 2 atmospheres. Let me actually write this down. 2 atmospheres versus 1 atmosphere of the, atmospheric pressure, right? What do we need to do to get it back down to that atmospheric pressure? Should the pressure on the inside increase, or should the pressure on the inside decrease to bring it to atmospheric if we had 2 atmospheres as the pressure on the inside? I'm asking, by the way. Yeah, so if the pressure on the inside increases, right, let's say to a point that's 2 atmospheres, right, and the pressure on the outside, right, we know that the lid is trying to maintain that atmospheric pressure, and the pressure on the outside is 1 atmosphere. What do we need to do on the inside, right, to essentially get back to that atmospheric pressure? Should we increase or decrease the pressure? Decrease, right? So we need to decrease the pressure on the inside. Well, how do we decrease the pressure on the inside? We don't have like an external machine that could adjust the pressure. But what happens is that there's an increase in volume. The molecules are kind of pushed up on the piston, right? And so with that increase in volume, that positive delta V, right, we know that pressure and volume are inversely related, right, based on the ideal gas equation. So an increase in volume then, a positive delta V, if they're inversely related, if one goes up, the other goes down, right? So if we see an increase in volume, we should see a decrease in pressure, which is exactly what we want, right? So the piston gets bigger, it expands, right? Volume gets bigger in order to bring that pressure back down to the atmospheric, that constant atmospheric pressure we want, right? Now, if the pressure on the outside, the atmospheric, happens to be greater than the pressure on the inside, so if the inside is 0.5 atmospheres, right, and that's less than the atmospheric pressure that we want to be maintained by the lid, which is 1 atmospheric pressure, right, then we would have to decrease the volume. Why? Well, if they're inversely related again, if you decrease volume, you increase pressure. So we want to increase that pressure on the inside back to that atmospheric pressure, right, to maintain a constant pressure, which is exactly what we're looking at for enthalpy. Remember, we want to maintain constant pressure and temperature. We're keeping that heat source there, boiling the water, right? Constant temperature, and we maintain that constant pressure by different increases or decreases in volume, right, for the gases when they push on the piston, right, or when the piston kind of presses down to decrease the volume in order to increase pressure, obviously. But that's the idea of enthalpy there, right? That's a situation in which you would use enthalpy when you have constant temperature and pressure, but changes in volume, right? That would enable PV work. Now, what does a positive or a negative enthalpy mean? So positive enthalpy means an endothermic process, so heat is input into the system. And negative enthalpy is an exothermic process where heat is released to the surroundings, right? So that's what enthalpy is so far. Any questions you guys have about maybe the useful, unuseful energy stuff, any of that? I see one, no questions. Anybody else? Nope. All right. Fair enough. Now, what is Helmholtz free energy? Right? We already covered what enthalpy is. Right now we can move on to Helmholtz free energy. This is another form of free energy, and we use it or analyze it when we have constant temperature, right? But now the volume and the pressure are changing, and we define this, or the variable for it is delta F, right? A little counterintuitive. Helmholtz starts with an H, but it's not delta H, it's delta F, right? So if enthalpy was constant temperature and pressure with changing volume, Helmholtz free energy is we have constant temperature, but the volume and the pressure are both changing, right? Now, usually when a system is put into contact with the environment at some specific temperature, right, then the system can extract energy from the environment, for example, right? So a really good example of this is what I mentioned earlier. If you have an ice cube, right, you put that ice cube in an environment that's going to be at a higher temperature, for example, right? Well, that system can extract energy from the environment, right? The energy can flow back into the ice cube then, and that heat flow from the environment into the system can increase entropy of the system, right? And that makes sense because, like we said, if entropy is related to the number of microstates, the number of ways we can distribute energy, the number of positions that particles can take up in a container, we can think about ice cubes as almost kind of being containers, right? Where everything's tightly packed. Well, then, if we want to increase the ways we can distribute those particles and increase the ways we can distribute the energy of those particles, then we're increasing the microstates. And therefore, if entropy is related to the number of microstates or the natural log of the number of microstates, like we said, or the multiplicity, then we're going to be increasing entropy, right? And once again, if you think about entropy with that older definition where it's a measurement of disorder, well, if you have particles tightly packed, organized like this, right, and then all of a sudden they're everywhere, well, they're more chaotic, more disordered, quote unquote, right? And they're essentially able to take up more microstates, more positions, more ways that they can distribute their energy, right? Now, in Helmholtz free energy, there is transfer of unuseful heat. Remember, enthalpy had no transfer of unuseful heat. But in Helmholtz free energy, there is transfer of unuseful heat. Now, unlike enthalpy, remember enthalpy had PV work, and that was unuseful work, right? Work here is controlled. In the situations or the scenarios that we're looking at Helmholtz free energy, work is often controlled, right? And so it's not factored into the change in free energy that we see. So the change in the free energy, the Helmholtz free energy in this case, can be defined as being equal to the change in the internal energy minus just the unuseful heat, right? Just the unuseful heat. And so that gives us delta F is equal to delta U minus T delta S. Well, you might be thinking, well, where the hell did we get or go from Q unuseful to T delta S, right? Well, the heat that flows into the system is defined as Q. We know that heat is Q, right? We also know from a previous chapter that delta S, the entropy, can be defined as Q over the temperature, right? So if we want to isolate for Q or rewrite Q, we can redefine it as Q is equal to delta S, or delta T. Q is equal to T delta S, basically, right? And so then that is the heat that we can get from the environment that flows into the system, right? That's where we get that term minus T delta S right there. So it's minus that Q, where that Q is equal to T delta S, right? Because delta S is equal to Q over T. So if you just multiply over the T, T delta S gives you Q. And so you take delta U minus T delta S, and then you're golden, right? Now, the Helmholtz free energy, this type of free energy, only results in a change in volumetric entropy, right? Because the temperature is constant in this case, right? Because the temperature is constant, then the internal energy is not changing, right? Because remember, internal energy, 3/2 NKBT, right? So if we're finding the change, like TF, right, minus TI, well, the temperature isn't changing, then the internal energy is not changing either, right? Now, at the same time, the number of molecules are not changing, or we're assuming that the number of molecules are not changing, and the degrees of freedom are not changing either, because that internal energy is not changing. So for Helmholtz free energy, when we're analyzing Helmholtz free energy, the only type of entropy that should be changing would be volumetric entropy, right? And it's kind of a snapshot there from the textbook. But yeah, honestly, like I said, you can just, if you understand where this equation is coming from, what delta F is, what delta U is, what this is, where it comes from, how to rearrange the variables and stuff, you should be good. But yeah, I think that covers the Helmholtz free energy stuff. Let me see here if I wanted to say anything else real quick. But yeah, any questions about Helmholtz free energy? If I kind of pause in between, I'm just drinking my coffee, so I apologize. Yeah, drinking coffee this late. Yeah. Yeah, so for volumetric entropy, right, Helmholtz free energy only results in a change of volumetric entropy. The reason why is, if we're looking at entropy of a gas in general, we know that it's the sum of the volumetric entropy and the energetic entropy, right? Well, if we're looking at energetic entropy, and we know that energetic entropy is Kb ln your total of the total degrees of freedom raised to the total energy blocks that you have. Well, if you're not changing the temperature, right, you're not changing factors like the degrees of freedom, right? Because remember, degrees of freedom, if you have a higher temperature, for example, then those particles will be able to move a lot more, right? They'll be able to distribute their energy in more ways, so they'll have higher degrees of freedom. So if the temperature is kept constant, degrees of freedom are not changing, and obviously if we're assuming that the number of molecules as well is not changing, usually that's the case, then energetic entropy does not change either. And we could also initially state that, well, if the temperature is not changing, then the internal energy is not changing. So the reason why Helmholtz free energy involves only a change in volumetric entropy is that since that temperature is kept constant, right, then you don't have more degrees of freedom to work with, right? If you remember that graph in one of the homeworks where it was like 3 degrees of freedom, 5 degrees of freedom, 7 degrees of freedom, it was like 3 halves NKBT, 5 halves NKBT, and then 7 halves NKBT, and then it was kind of like this, something like that. Like it was a step kind of function. And so if, for example, you were to keep that temperature the same, right? If this was your initial state, this was your final state where you're keeping the temperature the same, then you haven't changed the degrees of freedom. You haven't gone from 5 to 7 or from 5 to 3. And if you aren't changing your degrees of freedom, right? Remember we said that energetic entropy is Kb ln total degrees of freedom raised to the number, or the total number of energy blocks. If we're not changing the identity of the molecules, we're not changing the number of molecules, and we're not changing the temperature, right? That temperature, lack of a temperature change, will not enable, let me say that again. So no temperature change will mean that you're not unlocking new degrees of freedom, and you're not stepping down to lower degrees of freedom either, right? You're keeping the temperature constant. And so temperature constant, degrees of freedom constant. If the degrees of freedom aren't changing, the number of molecules aren't changing, and, right, the fact that, you know what? Let me start over real quick because I thought of a better way to explain it. So if you remember this idea of degrees of freedom and energy blocks from the previous chapter, you know that your internal energy, the total energy that you have, let's say, let me keep the delta out for a sec. Your total internal energy can be split into energy blocks, right? Different energy blocks. Those energy blocks can be split into or distributed into different quote unquote energy containers. These energy containers, right? Energy containers are kind of like our degrees of freedom, right? So we have a certain total internal energy. That internal energy is split up into energy blocks, and those energy blocks are distributed into degrees of freedom, different energy containers, quote unquote, right? Now, in Helmholtz free energy processes, temperature is not changing. Temperature is constant, right? Well, U is defined as 3/2 NkBT, right? For an ideal gas, at least. So internal energy is solely dependent on temperature. If the temperature is not changing, your number or your total internal energy is not changing either. Well, if your total internal energy is not changing, right, then the number of energy blocks you split that internal energy in is not changing either. So if you had 30 joules, right, and you split them into 6 energy blocks, well, considering the fact that you haven't changed the temperature from like 30 to 60, right, then you haven't changed the number of energy blocks. Well, if you haven't changed the number of energy blocks, right, and considering the fact that with higher temperatures, there's more movement of the particles, there's more ways to distribute the energy, there's more quote-unquote energy containers, there's more degrees of freedom at higher temperature. If that temperature is constant, we're not unlocking new degrees of freedom. We're not changing the ways that the energy blocks are distributed. So when temperature is constant in Helmholtz free energy, internal energy is not changed. Therefore, the number of energy blocks that we split that energy doesn't change either, because if we haven't changed the total number of energy, or the total energy, we haven't changed the number of blocks that we're splitting that energy into, right? And so if we did it in numbers, if we had 30 joules, right, let's say each energy block is 10 joules, right, where we have 3 energy blocks, right, 10, 10, 10. Then we can split, actually, let me write it this way. So if I did 30 joules as my total internal energy, I split that into 10 joules, 10 joules, 10 joules, 3 energy blocks, 3 Qs, right? Those can go into my 3 energy containers, my 3 degrees of freedom, right? Now, if I don't change this internal energy, right, then my Qs are staying the same. Let's say I want every single energy block to contain 10 joules, right? If I don't change this internal energy, right, and given the fact that I want each energy block to be 10 joules, for example, then the number of Qs don't change. And considering that increasing temperature unlocks more degrees of freedom, more ways, remember, like freedom, right? You're free to move. A higher temperature enables more ways you can distribute the energy, more energy containers, more ways, right, that the energy can be distributed. And so if that temperature is constant, then these energy containers are constant as well, right? So we have 10, 10, 10. Well, that's if everything is constant. Now, if I were to increase the internal energy, actually, you know what? Let me keep that part to the side there, safe for a sec. If I were to increase that energy from 30 to 60, right? Well, if I want each one of those blocks to contain 10 joules, it would be like 10, 10, 10, 10, 10, 10, right? And now I have to split them up into energy containers. Well, at a higher temperature, I might have opened up more degrees of freedom. Usually we're dealing with 3, 5, or 7. So let's say maybe I had 3, 4, 5, 6, 7. To where I have 10 here, 10 there, 10 here, 10 here, 10 here, 10 here, 10 here. Or yeah, there we go, right? So higher temperature opens up more ways I can distribute the energy, more degrees of freedom, increases my internal energy, and can increase my energy blocks. But considering the fact that the temperature is not changing, right, then the way I split up that energy into energy blocks doesn't change. Constant temperature gives you the same internal energy. Same internal energy, we split it up into the same number of energy blocks. Same number of energy blocks with that same temperature, right? No extra degrees of freedom, right? No extra energy containers, right? So if F doesn't change, Q doesn't change, and we're assuming the number of molecules don't change either, right? We didn't add any molecules to the system, then your energetic entropy, KB ln F power Q, where this is F total and this is Q total, right? And sometimes we even like multiply them by the number of total molecules, right? Well, if number of molecules aren't changing, degrees of freedom aren't changing, energy blocks aren't changing, then you should see no change in the energetic entropy. Does that make sense overall? The blocks of energy don't serve as storage themselves. It's the degrees of freedom that serve as storage. The blocks of energy are what we want to put inside those degrees of freedom. But does that make sense how I came up with the idea that, well, I didn't come up with it, but how we came up with the idea of the energetic entropy not changing, and so therefore the only type of entropy that's changing here is the volumetric entropy? Because, you know, you could, in the Helmholtz free energy process, right, the volume and the pressure are changing, and so if the volume is changing, your volumetric entropy has to change, right? So volume is changing, it's in the name, volumetric entropy. Volume has to change, but considering temperature is constant, your energetic entropy is not changing. Okay, awesome. Good old Gibbo. Before I move on to Gibbo here, any questions about Helmholtz free energy again? Nope. Okay. All right. So let's get on to Gibbo. So Gibbs free energy here is probably one of the most common forms of free energy that you've seen. You've probably seen it in your bio classes, you've seen it in your chem classes, you've seen it everywhere. But it's a form of free energy used or analyzed when we have constant temperature and constant pressure, right? Constant temperature and constant pressure. Remember, Helmholtz free energy had only constant temperature, but the volume and the pressure were changing. Enthalpy just had constant pressure and temperature, but a changing volume, right? Now, Gibbs free energy, constant temperature and constant pressure, right? And in Gibbs free energy, there's transfer of both unuseful heat and there is unuseful work being performed as well. So if you remember from the enthalpy, right, we had unuseful work, but we didn't have unuseful heat. In Helmholtz free energy, we had unuseful heat, but we didn't have unuseful work. Gibbs free energy is kind of like the combination of both. right? And so the setup for it is that it's equal to the change in the internal energy minus the unuseful heat minus the unuseful work, right? Well, once again, if we define that unuseful heat, right, remember we said delta S is equal to Q over T, right? So T delta S is equal to Q. So we can write it as delta U minus T delta S, right? That's the initial part there. Well, we can also say the unuseful work is P delta V, right? But this becomes positive because it's minus negative P delta V, right? Remember we said that earlier. So what you notice here is that delta U plus P delta V, that's just enthalpy, right? So we can simplify it down even more to delta G, the Gibbs free energy, is enthalpy minus T delta S. And that's where we get that very common, famous equation for Gibbs free energy, right? Any questions so far about Gibbs free energy? All good? Okay. The only thing that I might have to go back and edit, I think I might have made a mistake, but I want to go back and check it later, is the enthalpy. I think I added, so constant pressures for sure, but I think I might have added temperature as well. Yeah, I think that was a mistake. Yeah, that was a mistake. Because it doesn't make sense, because if you're using that boiling example, right, you're bound to be increasing the temperature of the system anyway, or changing it. So I will go back and edit this part out. So to kind of recap that again, enthalpy is constant pressure changing volume, right? Helmholtz free energy is you have a constant temperature, but the volume and the pressure are changing. Gibbs free energy is constant temperature and constant pressure, right? And the way you can kind of like check this, and this is why I checked it here, and I realized it didn't make any sense, is that if you're looking at the equations, well, you can see here that delta G is made up of the enthalpy minus T delta S, right? So we have constant temperature, there's no delta behind it. There's constant temperature and there's constant pressure, right? Because we know that enthalpy is delta U plus P delta V, right? So we have constant temperature, constant pressure. That makes sense for Gibbs free energy, and that matches up. For Helmholtz free energy, we just have a constant temperature and that's it, right? That makes sense as well, right? But for enthalpy, if we go back and check, we only have a constant pressure here. So I believe this should be changed. I'll mark that out. I'll edit it and re-upload the proper definition for that. But just wanted to clear that up as well. Now, there's another way kind of to think about all these different types of free energies, and I can go over that here real quick. So enthalpy, delta H, we can think about that as the total energy needed to create a system or the energy that we could recover if the system was destroyed. And these are all going to be very, very similar to each other. Helmholtz free energy can also be defined as the additional energy as work, right? Additional energy in the form of work, because remember we said that we're controlling the work in Helmholtz free energy situations. It's the additional energy needed as work to create a system or the amount of energy we could recover if we destroy the system. Gibbs free energy is the energy needed to create a system, right? Or the energy that could be recovered after destroying a system, right? After losing energy doing work and gaining energy due to heat flowing from the environment. Now, once again, just kind of like background stuff, theoretical stuff. You don't have to fully understand or like define this different way of thinking about the free energies, but it's nice to know. Yeah, I'm just one of those people that's very thorough, and I think you should make sure that you know as much as you can, because you don't know what they might ask you to explain on the exam or quizzes. Internal energy. It's not a type of free energy, but I think it was worth mentioning how they defined internal energy in the book as well. So internal energy is the total internal energy the system will have after it's created, right? But yeah, that's about it for how those free energies and how internal energy is defined in different ways in the book as well. Now, this is a recap of when we use each type of free energy. And I think I did it wrong at first, and then I fixed it later on for enthalpy. So enthalpy, you have an isolated system that can expand. It can expand. It's constant pressure. You have a changing volume, therefore you have PV work. And there's no transfer of heat. Right? Now, Gibbs free energy, it's constant temperature and pressure, and the system can expand and change heat. So the volume can change, and you can exchange heat as well. Helmholtz, you only have constant temperature. So this is constant temp, this is constant pressure, and this is constant pressure and temperature. So those are the different free types of energy, different types of free energy. Now we can try to think about, okay, well, how do these free energies relate to the concept of equilibrium, right? So let's address first enthalpy in its relationship with equilibrium. So generally, right, you don't really have to, I guess, maybe know physics to understand this, or at least kind of think about this, but if a system loses energy, right, if a system loses energy, we can say that the environment gains that energy, right? Whatever energy is lost by a system is gained by the environment, right, to make sure that the energy is fully conserved. So, an increase in energy would cause an increase in entropy of the environment, right? So if the environment is increasing in energy, it increases the entropy of the environment. Why? Because you have that increase in energy, right? Let's say, for example, what was I going to say? No, I totally blanked out. I lost my train of thought. Yeah, so increase in energy increases the entropy of the environment, because let's say if heat is given off, right, from a system to the environment, well then maybe the gas molecules around that system in the environment will have that energy absorbed, right? And so then they could essentially be excited, basically, and they could have increased temperature, increased kinetic energy. They could take up more positions in the environment. They can distribute their energy in more ways, right? And so if you're distributing energy in more ways, you're taking up more locations, more states in the environment. You're increasing your microstates, you're increasing your multiplicities, and therefore increasing the entropy, right? If a system decreases in volume, you can kind of say that the environment gained in volume. So it's kind of an opposite relationship here. So if you lose energy, if the system loses energy, the environment gains it. If the system decreases in volume or loses volume, the environment gains volume, right? And so an increase in volume, right? An increase in volume will increase the entropy of the environment as well. Think about that with energetic entropy, right? If we increase the volume of the container, right, increase the volume of the environment, basically, then we increase the entropy of the environment. The idea is, right, that any change in entropy that the system experiences, the system will only experience a very small change in entropy relative to the entropy change that the environment experiences. Now, as we mentioned before, a system in the universe will tend to evolve towards states of higher entropy. They want to increase their entropy, right? So if we're trying to achieve this maximum state of entropy, right, and we mentioned the maximum state of entropy is at equilibrium. Well, to maximize entropy, if holding these two conditions to be true, right, that increasing in energy increases entropy and decreases in volume, or increases in volume, will increase the entropy. So if increase in energy increases entropy and increase in volume increases entropy, then it would only make sense that the internal energy of the system should be decreased and the volume should be decreased to maximize the entropy of the universe. Now, what does that mean? Because that is a little confusing there, because if we said increase in volume increases in entropy, then why are we decreasing volume, right? Well, it's kind of a balance. We don't want the system to experience a horribly huge change in entropy. But at the same time, right, we want to make sure that the universe is increasing a lot in entropy. So, if we increase, if we decrease the internal energy of the system, right, decreasing the internal energy of the system means that energy is flowing out of the system, right? So the system has a certain U, certain internal energy. If we decrease that U, energy flows out of the system and into the environment, increasing the energy of the environment. Remember, it's an opposite kind of relationship. So if you decrease the internal energy of the system, you're increasing the energy of the environment, right? Now, if you decrease the volume of the system, you're increasing the volume of the environment. And if you increase the volume of the environment, you increase the entropy of the environment. So, once again, if you decrease the entropy of the system, you're not the entropy, my bad. If you decrease the internal energy of the system, you're increasing the internal energy, or energy essentially, of the environment, right? Or the universe, right? And if you're increasing the energy of the universe in that case, with that kind of opposite relationship, right? If you're increasing the energy of the universe, then there's more ways to distribute that energy now, and kind of all the same things that I was talking about with entropy before, right? So more ways to distribute energy, more places that the particles can take on, right? Or more locations that they can take on. And so therefore, you have an increase in entropy. So if we decrease the entropy of this, or if we decrease the internal energy of the system, we increase the internal energy, or the energy of the universe, right? And therefore increase the entropy of the universe, right? We can do the same with volume. If we decrease the volume of the system, we increase the volume of the universe. And if we increase the volume of the universe based on volumetric entropy, then the volume of the universe container basically is increasing, and therefore your entropy of the universe is increasing as well, right? So it's an opposite relationship. Now, if you're decreasing the internal energy of a system and you're decreasing the volume of the system in order to increase both of those values for the universe, then you realize then if U is down and V is down, then enthalpy is at a minimum. Because remember, enthalpy is delta H is equal to delta U, right? Plus P delta V. So if U is brought down and delta V is brought down, both of those terms decrease, basically. And so delta H is consequently brought down as well. So delta H is at a minimum when we're trying to reach equilibrium. Because remember, equilibrium means we're trying to increase the entropy. So as we increase the entropy of the environment, right, we are going to be decreasing values like the volume and the energy of the system. So like I said, decreasing the energy of the system increases the energy of the environment, increases the entropy of the environment, right, or the universe. If you decrease the volume of the system, you increase the volume of the universe or the environment, and therefore you increase the entropy of the environment, right? So, with the volume of the system being down, and with the energy of the system being down, then delta H, with the equation being delta U plus P delta V, if both of these are down, decreasing, right, then delta H is at a minimum, because as we try to increase that entropy more, we're going to decrease that energy in the volume even more, right? The more we decrease the volume and the more we decrease the internal energy of the system, the more we increase the entropy of the environment. And we want to maximize that entropy. If we maximize the entropy, we minimize the internal energy and we minimize the volume, right? If we minimize the volume and we minimize the internal energy of the system, we therefore minimize enthalpy. So enthalpy is at a minimum, right, at equilibrium. So that checks off the relationship between enthalpy and equilibrium. Now, how about Helmholtz, free energy, and equilibrium, right? Well, as we defined before, or actually, we defined it in a previous chapter, I believe, but the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the environment. And that has to be positive, right? Because we know that the entropy of the universe is going to be increasing. We also know that delta S is equal to Q over T. We mentioned that earlier, right? Well, in scenarios where we have Helmholtz free energy, right, we know that transfer of heat is allowed. Heat transfer is allowed. And so if you think about heat transfer in general, the energy absorbed by the environment is the energy lost by the system, right? And if energy is lost by the system, we can say that, well, the system lost internal energy, right? So if we write this kind of expression here, Q environment, the energy absorbed, the heat absorbed by the environment is the heat lost by the system, and that means energy, internal energy lost by the system, right? Then, if we have this expression and we simply divide by temperature all the way around, right? Because remember, delta S is equal to Q over T. So if Q over T is equal to delta S, we can actually convert all of these to entropy values. If we divide all of these by temperature, we get values of entropy, right? So Q environment over T would give us the delta S of the environment. Negative Q system over T would give us negative delta S system, right? This is delta S environment. This is negative delta S system. And then this gives us negative delta U system over T, right? We can just leave that as is for now. Now, let me actually move on to what I had in this drawing here, right? So like I said, if we were to just simply divide by T for every single piece of that, right? Let me just kind of highlight what's going on here. So when we divide it by T for that specific, actually let me use a highlighter or something. Is that a, no, doesn't look like it's a highlighter, I guess. And that's a crayon. All right, screw this. I'll just mark it up with a different color. So this part right here, if we divide by T to get delta S, then we get Q environment divided by T is delta S environment, right? And then negative Q system divided by T gives us negative delta S system, and negative delta U system divided by T is just negative delta U system divided by T. Now, if we rearrange things and use this initial equation, right? S delta S universe is equal to S system plus S environment. Well, S environment, right? We said that was equal to negative delta U system divided by T. So we can plug it in. We can say delta S universe is equal to delta S system minus delta U system divided by T. If we multiply by T all the way around, we can cancel out this T. We have T delta S universe, T delta S system minus delta U system. What do you notice about this equation right here? Well, you should notice that it's the exact opposite of the Helmholtz free energy equation. Helmholtz free energy equation was delta U minus T delta S of the system. This is negative delta U plus T delta S of the system, right? So it's exactly negative delta F. It's exactly negative delta F. So we can see here that T delta S universe is equal to negative delta F. Well, what does that mean? Let's go back. If T delta S universe is equal to negative F delta F, right, of the system, negative change in the Helmholtz free energy, then delta F, that Helmholtz free energy, has to be negative. The change in the Helmholtz free energy has to be negative to make delta S universe positive, right? To make this term positive. If we want this left-hand side to be positive, delta F has to be negative. So it'll be negative times negative delta F, right? So you have positive on that right-hand side to make this left-hand term positive. And we want to make delta S universe, right, the entropy of the universe, positive and as big as possible, because that's what we're going for any thermodynamic system. We want to make sure that there's an increase in entropy for the universe, right, and achieve that maximum entropy. So that way, the entropy of the universe increases and we're achieving that maximum entropy if we make that Helmholtz free energy change negative, right? So, like I said, system evolves in a way to minimize then Helmholtz free energy at equilibrium, right? If we make, technically, right, if we make that delta F as small as possible, right, as negative as possible, then we maximize T delta S term. And therefore we maximize delta S, essentially, right? So if this is as negative as it can be, as small as it can be, then negative with a negative, right? If this is like negative 1,000, right, then you just made that term on the left-hand side really big positive term. And that's what we're looking for. So essentially, for Helmholtz free energy, what we're experiencing when we're achieving equilibrium is a minimization of Helmholtz free energy. So if for that enthalpy situation, right, as we approach equilibrium, as we're trying to achieve that higher state of entropy, we minimize enthalpy. Same goes for Helmholtz free energy. We minimize Helmholtz free energy to maximize our entropy, right? To minimize Helmholtz based on the equation, right? What was it again? Delta U, I kind of forgot. Delta U minus T delta S, that's what it was, yeah. So if it's delta U minus T delta S, right, we can decrease the internal energy and we can increase the entropy term, right? We want to make that negative, like this part right here, this negative T delta S as big as possible and delta U as small as possible, right? That way, delta F can be as negative as possible, and if it's as negative as possible, negative and negative, will give us a very large T delta S term, and that would increase the entropy as much as possible, which is what we're trying to achieve when we're going for equilibrium, right? Now, finally, with Gibbs free energy and its relationship with equilibrium, right? I remember that Gibbs free energy, both work can be done on the system and heat can be transferred as well, right? So the environment can acquire energy from the system via heat, or it can essentially acquire volume from the system, as we mentioned before, right? So we mentioned that you can either decrease the internal energy of the system, therefore increasing the energy of the environment, or you can decrease the volume of the system and then increase the volume of the environment, right? Now, those are the ways that essentially you can maximize the entropy of the universe once again, right? If we decrease the energy of the system, we increase the energy of the environment. If we decrease the volume of the system, we increase the volume of the environment, right? And so increases in volume and increases in energy of the environment would increase the entropy, as I mentioned before, right? So the more you decrease the internal energy and the more you decrease the volume of the system, essentially the more we maximize the entropy of the universe. Now, considering that delta G is equal to delta H minus T delta S, as we mentioned before, and we also said that we got to kind of expand it to be, well, if delta H is delta U plus P delta V, right? We can say that delta G is delta U plus P delta V minus T delta S, right? So you can see from this expanded equation that if we're decreasing delta U, decreasing delta V, and increasing delta S, right? Because that's what happens when we're approaching equilibrium. We're trying to decrease the energy of the system to increase the energy environment, decrease the volume of the system to increase the volume of the environment, and therefore increase the entropy, right? Then that makes delta G as small as possible. So once again, when a thermodynamic system evolves to achieve a higher state of entropy, to achieve equilibrium, we're also going to see that Gibbs free energy is sacrificed and brought to a minimum to achieve that equilibrium. And at equilibrium, delta G just so happens to be 0. Now, we could also ask, because delta G has a very strong relationship to equilibrium as opposed to the other two types of free energy, and we can ask ourselves, well, what does delta G, or what impact does delta G have on reaction rate, right? And that is none. No impact whatsoever on the reaction rate, how fast the reaction occurs. The only thing that delta G can tell us, based on its signs, is whether a reaction is spontaneous or non-spontaneous, right? So delta G is not related to how fast things happen. A negative delta G tells us that the reaction is spontaneous. A positive will tell us that it's non-spontaneous, right? It provides no information whatsoever about the reaction rate. Now, this is a really, really good table to go over. Super, super important, because you're bound to get a question like this either on the quiz or the exam that will be more conceptual. And it's essentially the different combinations of delta H, delta S, and temperature that will achieve a negative or a positive delta G, right? That would indicate whether a reaction is spontaneous or not spontaneous, right? So I remember an equation that I got on a problem that I got on the exam, I think. It was like, if you have positive enthalpy, and let's say positive entropy, for example, is the reaction always spontaneous, sometimes spontaneous, or non-spontaneous, or something like that. So you had to kind of like have this table memorized essentially, or be able to like manipulate values during the exams to figure that answer out. So I strongly recommend kind of memorizing these. It's not too bad, because you're bound to get an equation or bound to get a problem like that that's a little bit more conceptual. But yeah, this is a really good table to look at. It tells you like, okay, if delta H is negative and delta S is positive, then that means delta G is always negative, right? Or for example, if delta H is negative, right? If you have a negative delta H and a negative delta S, right? Negative delta S, then that T delta S term becomes minus T times negative delta S, right? So that becomes negative delta H plus T delta S. So this term, if it's bigger than this term, then you have a positive delta G. So that means at really high temperatures, it is non-spontaneous. But on the other hand, if the temperature is super, super low, right, low temperatures, then the delta H term could actually be bigger. And therefore, at low temperatures, you would have a spontaneous reaction because delta G would be negative at that point. Highly recommend going over this table. Now, how can we use delta G to figure out the direction of a reaction? Very similar to like comparing reaction quotients in equilibrium expressions back in Gen Chem. You just compare the delta G value to the equilibrium delta G value. So if delta G is greater than the delta G at equilibrium, reaction proceeds to the left. If it's less than, it proceeds to the right. And a nice tip and cool way that I came up with when I was peer leading Gen Chem students is you can kind of look at the less than or greater than signs, like what direction they're open. And I used to call them alligator mouths, right? So whatever direction the alligator mouth, whether it's less than or greater than, is open, whatever direction it's open in, is the direction the reaction proceeds in. So if the alligator mouth is open to the left, reaction proceeds to the left. If it's open to the right, it proceeds to the right. This hinges on putting your equilibrium value on the right. So let's say if it's like Q greater than K, I make sure like whatever equilibrium expression, whatever equilibrium constant is on the right. That way this tip always works. So if Q is greater than K, reaction proceeds to the left. If Q is less than K, the alligator mouth is open to the right, so the reaction proceeds to the right, right? That's a nice tip there to figure the direction of the reaction out. Speaking of reaction quotients and equilibrium constant expressions, right? They're just ratios of the product concentrations to the reaction concentrations. Once again, if Q is less than K, proceeds to the right. Q is greater than K, proceeds to the left. And it's basically each of your products raised to the power of their coefficients, right? Multiplying together, divided by the reactants raised to the power of their coefficients, multiplied together. Same thing for the equilibrium expression there. Now, the reason why I bring those concepts up is that there's a relationship between delta G and equilibrium with an equation, and that's delta G, right? The value of delta G that you're looking for is equal to the standard delta G of formation plus RT, where R is your ideal gas constant, T is your temperature, times natural log of your reaction quotient, right? That tells us the delta G at any specific point. At equilibrium, however, right, we know that delta G is 0 at equilibrium. I mentioned that earlier, right? So if delta G is 0, then the standard Gibbs free energy is equal to negative RT ln KEQ. So instead of ln Q, where it's your reaction quotient at any stage of the reaction, you replace it with KEQ, which is your equilibrium, because we already set delta G equal to 0. So I said delta G is at a minimum at equilibrium, and it's equal to delta G is equal to 0. That wraps up the week 5 content review. I don't know if you guys have any questions so far about this content, if there's anything you want me to go back to. But yeah, that covers everything that you guys need to know for week 5. Like I said, I strongly recommend going over the practice problems for that are in the reading. So let me see if I can bring those up here real quick to show you guys. So this is chapter 5. So if you take these practice problems here, they're explained in very high detail, right? They relate everything back to the concepts that are taught and all of that. And I think they're really nice to help build conceptual knowledge and apply that to problem solving. At the same time, I'm telling you this right now, this is like, I'm not lying. Some of these problems that are in the practice, or that are in the reading, these practice problems that are in the reading, sometimes they're like, I won't say copy and paste, but like they're very close, same setup, same types of questions that they're asking you on these quizzes. When I started reading the readings in 132, at first I was doing like the professor's like slides and stuff. Those didn't work out for me. So when I started doing the readings, when I did these practice problems and I made sure that I understood every single one, it helped a lot with getting my quiz grades up. So definitely recommend going over those. Some of the problems like are a little overkill. Let me show you. And like some of the concepts are a little weird. Like I think I just skipped over this section here about elastic forces and free energy. Like you can see, I barely took any notes on it, just like random highlights. It's not super necessary. It's a very niche type of situation that I'd say maybe look over once, maybe twice, just so you roughly are familiar with it. and they do give a problem about it. So I'd go over the problem as well, just so you at least know like what you're up against essentially. But it's usually the bread and butter is like the rest of the stuff. But like I said, it's nice to go over all those different types of practice problems so you're aware of what they're expecting of you. But that's pretty much it. And if you go, there's an answer key at the very, very end with each quick check explained, each problem step by step explained, all of that. So highly, highly recommend you guys going over these. In the future, like I said, I'm moving around some of my sessions. I have to reorganize some things with my sessions because I won't be holding any written homework reviews anymore or the online homework. And I'll only have content reviews pretty much. So I will try and essentially integrate these problems in the content reviews in the future. So hopefully, right, that we can go through them together and that can help you guys kind of get an idea of how to go through that stuff and what to expect on quizzes and whatnot. Will I still have drop-in hours for homework? More or less, I'm just going to avoid touching the homework. I'm just going to be honest. I don't want to mess with that anymore. I've no place to mess around with my schedule anymore at this point. So unfortunately, I'm probably just not going to touch the homework. If you guys have questions, once again, I will try my best to get back to you guys. There's a couple people that DM me for the last homework, so that's fine. I can look over some things and help answer questions and stuff, but I just don't want to hold like a formal drop-in session again because I just want to be safe and make sure that I'm not like breaking any rules or anything. So I just want to make sure that like I'm providing as best support as I can, as much support as I can without like, I guess offering too much detail. And I guess maybe sometimes I'm too nice of a person or what. Maybe I'm too nice for my own good, but yeah, I tried for the last session to be a little bit more general, but it's fine. Like I think I'll stray away from doing the homework reviews. So yeah, no more homework reviews that are detailed at this point. But I'll see if I can have like an extra drop-in session for general questions about the concepts. But I'm not going to discuss homework reviews. I'm not going to discuss not homework reviews. My bad. I'm not going to discuss homework problems directly. But if you have questions pertaining to the concepts about the homework, right? Like if you don't understand Helmholtz free energy, for example, like that was a concept on the homework, I could explain that. But like walking through step by step, addressing even like what the homework problems are about, unfortunately, I'm not going to be able to do that anymore. So, but yeah, I'll keep up with these content reviews. In the future, I'll go over some of those practice problems in the reading as well. I'll walk you guys through those. But yeah, just heads up with that. Please try and keep up with the readings as well on your own, because I think like if you read those readings before you even come to these sessions as well, it'll help with solidifying a lot of the concepts. So they're usually around 30 pages. Some of the reading, like maybe one or two readings in the entire semester are like 40. But if you spread them out, if you just take like 10 pages a day, and then like just review over the weekend, you should be solid. But yeah, I think I'm going to go ahead and end the recording on that note. And then I'll leave it open for questions.